Still talking about orthogonality and approximations. This video focuses on orthogonal projections and least squares. So this lesson covers projection onto subspaces, least squares up, least square solutions, geometric interpretation, some worked examples, and these ideas are central in linear algebra, data fitting, and data science. Of course, the idea of least square already should tell you something. So in the introduction, we see that orthogonal projection and least squares methods are used when a vector must be approximated using a subspace. A system of equations has no exact solution. So in some cases, we have no exact solution, right? We want the best fit model for data. So the main goals here will be to find the closest vector in a subspace and minimize error in linear systems. So we are approximating solutions to things that would not naturally not have solutions. So let's go straight to talk about projection onto subspaces. Thankfully, in the last video where we considered Gram-Schmidt's orthogonalization, we saw how to project a vector onto another one, using a very beautiful formula like that, dot products and all that. So projection onto subspaces, let V belong to the n-dimensional real number system and W be a subspace of the n-dimensional real number system. So the orthogonal projection of V onto W is the vector in W closest to V, and it is written as the projection of V onto W. So we are projecting onto subspace. We are projecting a vector onto a subspace. In under Gram-Schmidt orthogonalization, we saw how to project a vector onto a vector. Now we are saying how to project a vector onto a subspace. Okay, so we have some key properties of projection, key property of projection. First of all, if P is the projection of V onto the subspace W, then we can say that V minus P, that is when we remove the projection from V. So V minus P is perpendicular to the subspace itself. So this means the error vector is perpendicular to the subspace. So the difference between the vector and the projection, which is the error vector itself, is perpendicular to the subspace. And this guarantees that P is the closest vector to V in W. So P is the closest vector. That projection is the closest vector to the V in the subspace W. So we go on to talk about projection onto a line, which we have been used to already. We did that a lot, talking about the Gram-Schmidt process, or if you like, Gram-Schmidt orthogonalization. So projection onto a line. So let W span U, all right? And of course, U is a vector where U is a non-zero vector. U is not equal to zero. So this projection of V onto U is given as this. Projection of V to U is the same thing as V dot U, all right? V dot U all over U dot U multiplied by U. Of course, V dot U is scalar, U dot U is scalar. So you have this whole ratio is a scalar, but then this U is here to ensure that you still have a vector going. And by doing this, you would have projected V onto U. So this formula gives the closest point on the line spanned by U. So this is the closest point on the line spanned by U. Okay, so we talk about derivation. So let's talk about derivation now of the projection formula. So very straightforward. We want the projection to be C times U, right? Such that V minus CU is perpendicular to U itself. Okay, so in that case, now we see that V minus CU dot U is equal to zero because they are perpendicular, right? So V minus CU dot U will be zero. If we expand that, we see that V dot U, we have V dot U minus CU dot U. That's C into U dot U, and all of that is equal to zero. So if we solve for C now, okay, if we solve for C, of course, we can transfer C to the other side. So we have V dot U equals C into U dot U. At the end of the day, C is equal to V dot U all over U dot U. Now, this gives the projection formula. So in addition to this, now we just multiply it by the vector U to make sure it is in that U direction still. So that's for derivation of the projection formula. So how about an example to drive home the point? Example of projection onto a line. So if you want to project V, which is 2, 3, onto U, which is 1, 1. What do you do in that case? So the solution, first of all, you need V dot U, right? By the way, projection of V onto U, like we already know. So projection of V onto U would always be something like project v onto u, and that'll be v dot u all over u dot u multiplied by the u itself. Okay, v dot u all over u dot u multiplied by u. So that's the projection of v onto u. So that's the component of v that goes in the direction of u. So first you compute the dot product, the v dot u, which is 2 times 1 plus 3 times 1. 2 times 1 is 2, 3 times 1 is 3. So 2 plus 3 is 5. Then u dot u, that's 1 times 1 plus 1 times 1, that's 1 squared plus 1 squared, which is 2. And then you apply the formula. So projection of v onto u. So that'll be v dot u 5 all over u dot u 2, that's 5 over 2 into u itself, which is 1 1. So you have 5 over 2 into 1 1. So at the end of the day, that's 5 over 2 comma 5 over 2. So the projection is 2.5 comma 2.5, like that. So then we move on to talk about projection using an orthonormal basis. Projection using an orthonormal basis. So let the set U1, U2 up to UK be an orthonormal basis of W. That subspace we saw the other time. Then we say that the projection of V onto the subspace is equal to the summation from I equals 1 to K of V dot UI, multiply by ui. So it's like you can then have so for all these k vectors now, so you have v dot u1, all right, time plus v dot u2 multiplied by u2 plus v dot u3 multiplied by u3, and so on and so on and so forth. So this formula works only if the basis is orthonormal. So if this wasn't orthonormal, then this won't work. If it is orthonormal, all the vectors are already they have magnitude of 1. So they are all units, they have magnitude of 1. I think that's the best, it's one nice way to put it. Okay, so we can also talk about matrix formula for projection now. So what if we are dealing with matrices? So you have a matrix whose columns are made up of vectors u1, u2 up to uk. Then we can say that the projection of v onto w can be written as a into a transpose a, the inverse of that, multiplied by a transpose v. So this works for any linearly independent basis. So if you have, of course, you have to be sure that at the end of the day, this matrix formed here, is a linearly dependent, meaning that in echelon form, there's no zero row at all. So, and then we have an example of projection onto a plane. So for projection onto a plane, so V is 1, 2, 3. So onto plane spanned by U1, which is 1, 0, 0, and U2, 0, 1, 0. What do? We have the solution. The vectors are autonomous. Of course, you can see these vectors are orthonormal automatically because they are both orthogonal. 1 times 0, 0, 0 times 1, 0, 0 times 0, 0. So you add everything, you get 0. That's orthogonality guaranteed. For orthonormality, if you find the norm of U1, you get 1. Norm of U2, you get 2. So these are orthonormal. So the vectors are orthonormal for sure. So we can say that the projection of V onto W will just be 1, 2, 0. Okay, 1, 2, 0. And the Z component is removed. So I mean the projection here, we are projecting V onto W. So it's more like we have V. Okay, I guess I need to work that out. So to clarify, so V is 1, 2, 3, right? So we have V to be 1, 2, 3, and then we have U1. Okay, we have U1 to be 1, 0, 0. Okay, 0, 1, 0. So 1, 0, 0, and then U2 is 0, 1, 0. So what we are doing is projection of V onto the subspace. So projection of V onto the subspace W. Of course, that will be the summation of all these things. So we have V dot U1 all over U1 dot U1 multiplied by U1 plus V dot U2 all over U2 dot U2 multiplied by U2. So in that case, so okay, let's just go. Let me come here now. So the projection of V on the dot subspace is now this. So V dot U1 now. V dot U1, that is 1, 2, 3. 1, 2, 3 dot U1. U1 is 1, 0, 0. 1, 0, 0 all over U1 U1. So that's 1, 0, 0 dot 1, 0, 0 into 1, 0, 0 plus V again, that's 1, 1, 2, 3, 1, 2, 3, dot U2, 0, 1, 0, that's 0, 1, 0, all over 0, 1, 0, dot 0, 1, 0, multiplied by 0, 1, 0. That's U2 now. So that projection now, so up here we have 1 times 1, 2, 0, 3, 0. So we just have 1 here, all over 1 down here, basically, into 1, 0, 0, plus here 2, we have 1 times 1, 0, 1 times 0, 0, 2 times 1, 2, 3 times 0, 0. Then down here we have 1 into 0, 1, 0. So in that case now we have 1, 0, 0 plus 0, 2, 0. So finally, if we add it all up, we have 1 plus 0, 1, 0 plus 2, 2, 0 plus 0, 0. So that's how we got that particular result to be 1, 2, 0. So you can see now we only have x, y, z is gone to 0. And that is why this is said to be in the xy plane, because the z component is gone, right? So that's exactly what's happening here. Okay, so the projection of V onto W is 1, 2, 0. So the Z component is removed. This is the projection onto the XY plane. So in that case, now we're talking about projection onto a plane in that case. So having taken care of that, what we're talking about here is orthogonal projection and least squares, right? And least squares. So least square problems now, this is how that goes. So consider the system AX equals B, where A is an M by N matrix and X and then M is greater than N, right? So we have M greater than N. So M rows, N columns, right? So it means that we have M equations and N variables, okay? So we have more equations than we have variables. So in that case now, um, we are supposed to have, the system is supposed, it's going to be inconsistent because you have more variables than we have equations. So we are going to have yeah, we are going to have an inconsistent solution. No solution, in fact. So this system is usually inconsistent. So there's no exact solution. All right. So the motivation here is this. When no exact solution exists, we want AX to be, you just want to approximate A, we want AX to be approximately B. So we define the error now to be, the error will have to be AX minus B. All right. So this is not possible, but we just want to try, but that's going to give rise to some error, which is the difference between AX and B itself. And then we have to minimize that error, so that'll be the square of the norm of AX minus B. And this is called the least squares criterion. So you see where the least square is coming from. So least square. So this is the possible square, of the norm of AX minus B. And then we want to make sure it is as small as possible so that we can minimize our error, because we are doing something that is impossible and it will lead to an error, but we want to make the error to be as small as possible so that our efforts will still be worth it in some way, right? So let W, that's the subspace now, be the column space of A. Then we say that AX belongs to W, right? Then we want the closest vector in the subspace to B, all right? So that AX is the projection of B onto W. So you can see how the idea of projection is coming into least squares method now. And that's why how you can see how all of this whole thing will play into machine learning data science. In fact, after this set of videos, the next set of videos is going to be focused on data science, linear algebra in data science, linear algebra in network analysis, and things like that. So watch out for those videos coming. So we want the closest vector in W to B. So AX is projection of B onto W, and least in this case now we have least squares is equal to projection, right? So least squares is as good as talking about projection. Then we talk about the normal equations. So the error is perpendicular to the column space. So B minus AX is perpendicular to the column space. So if you remember what we did about column space the other time, it is actually that point where we have we solve AX equals B, right? So A transpose into B minus AX should actually be equal to 0. If you rewrite this now, we have A transpose A, all right? A transpose AX. I mean, if you expand this now, you have A transpose B minus A transpose AX. So you have A transpose AX equals A transpose B. So these are called the normal equations. So A transpose AX equals A transpose B. That's normal equation. And then we have the least square solution. So if A transpose A is invertible, that is, if we can take the inverse of A transpose A, so we can take the inverse of both sides. So the A transpose A inverse comes to this side, and A transpose A inverse cancels this side. So X itself will now be A transpose A inverse multiplied by A transpose B, like that. So this gives the unique least square solution. So in this case, now we have managed to find a way to approximate the solution to this problem that was supposed to not have solution originally. So let's look at an example right here. Simple least squares. Imagine you want to solve x is 1, x is 2, and x is 3 using least squares. So solution, so just have a matrix. So let your A be 1, 1, 1, because I mean we already know the solution is not possible. So let A be 1, 1, 1, and your B now, the right hand side is 1, 2, 3. So what do? Then we compute A transpose A, and that gives 3. A transpose B gives 6. And then we solve 3x equals 6, right? So for instance, I mean we want to solve this x 1, 2, 3 like this. So again, we have A to be 1, 1, 1, all right? A A is 1, 1, 1. Then B is 1, 2, 3. And based on what we need to do here, see this now. We need to take care of our X now will have to be A transpose A inverse, then multiply by A transpose B. So we have A transpose A, we get 3. A transpose B, we get 6. Okay. And at the end of the day, the best solution is 2. But I mean, let me do it my own way here. So I think the fundamental thing is just remember this, that A transpose A inverse times A transpose B, right? Okay. So A transpose A inverse. So we know that X will be A transpose A inverse, then A transpose B. How does that happen? So we know A is 1, 1, 1. So A transpose is going to be 1, 1, 1 like this. So it means that A transpose A transpose A is equal to 1, 1, 1 into 1, 1, 1. What that simply means is that, of course, this is just easy. You have 1, 1, 1. So this 1, 1, 1 will also come over it. 1, 1, 1. So this is equal to 1 plus 1 plus 1. And that is equal to 3. So A transpose A is equal to 3. So, well, because this is just a scalar, so it means that A transpose A inverse is equal to 1 over 3. So we leave that first. So we have got this part now. We need A transpose B. So what do we do for with A transpose B? So for A transpose B, A transpose is 1, 1, 1, and B now, we already know B to be 1, 2, 3. So we have 1, 2, 3. So I can take this down now. So this is one row. So you write this column once. So you have 1, 2, 3. Then you put 1, 1, 1 over it. That's the same thing I did in this other case. I didn't just say that, all right? So now this is 1 times 1, 1, 2 times 1, 2, 3 times 1, 3. So this is equal to 6. So with all of this in place now, we can then go ahead and say X is A transpose A inverse multiplied by A transpose B. So that means X is equal to A transpose A inverse. The inverse of 3 is 1 over 3. So we have 1 over 3 into 6, A transpose B. So the best answer in that case is X equals 2. And that's exactly what we have right there. So it's just like get the algorithm in order. So if you can remember, I think intuitively, if you can remember this, or better still, if you remember this, since we are looking for X at the end of the day. So once you have a system that cannot be solved, for instance, this simple one now that X is 1, X is 2, X is 3 makes no sense, but then you can just find a way to work around it. Okay, so we can also have least squares for line fitting, right? Least squares for line fitting. So we want to fit Y equals AX. It's almost looking like regression, right? So we want to fit Y equals AX plus B, or in fact regression. So to data points. So you have this line now and you have some data points. You want to fit it, and you don't have all the information. So data points X, I, Y, I. So first of all, you have the matrix form. So the other time we just had 1, 1, 1, 1 all through. So you can get all your X values x1, x2 up to xn. Then with all, then you just step it up with one by the side. Then x now is AB. That's the right. Oh, that yeah, those are the values of x, right? So in that case now, B, which is the right hand side, you always talk about ax plus b. So the right hand side now is y1, y2 up to yn. So imagine you want to do this now. Best line of fit. You want to fit a line 1, 2, 2, 3, 3, 5. So you have all the x1, x2, x3, y1, y2, y3. So 1, 2, 3, 2, 3, 5, like that. So what do you do? So you have all the, so from what we have here, you have all the x's, right? With 1, 1, 1 by the side. So you have 1, 2, 3 right here, then 1, 1, 1 here. So whatever you have here, you always have 1, 1, 1 here. And the right hand side is the y's, that's 2, 3, 5, like this. So what do we do? You need to find A transpose A. Okay, well, I mean, at the end of the day, you get that answer, and then you have the best line is 3 over 2x plus 1 over 3. Now, I jumped to that because I really want to do that. We are looking for A and B, right? Um, so this is A transpose A. Okay, or maybe I can just follow this through. So A transpose A means you have 1, 1, 2, 1, 3, 1. Um, okay. Let me go for that. I'm trying to reconsider if I should do it. Okay, that's fine. So 1, 2, 3, 1, 1, 1. You have, so here now you have A is 1, 2, 3, 1, 1, 1. So you always augment with that, right? And the B side is 2, 3, 5, I believe. The B side is 2, 3, 5, I think. That's 2, 3, 5. Yeah. And then, so the first thing we want to do now, we have okay, we have a case where this is equal to this, right? So we know that so in this case now, I mean the question will also determine, right? We want to find A and B. So we want to it's more like we want to solve this. We want to fit a line, and the equation is y equals ax plus b. So we need to get A and B, right? So where that is coming from is um given given the points 1, 2, 2, 3, 3, 5 fit to the line, fit to the line y equals ax plus b. So that will mean we need A and B, but we don't have enough information to make that happen. So we can then say that so we have A, we have B like that, and then of course we have y, right? So y, okay, A transpose A, A transpose B. Yes, except that now we are looking for this A and B. I don't want to get it all confused. So because, okay, this is A transpose B now, but then this AB here should not be confused with this B. Maybe I can just call this, yeah, but I mean, if you can just get the gist. Okay, so we know we have, yeah, we have A transpose. I guess I need to change this. We have A transpose A x is equal to A transpose B. Generally speaking, this is what we have. So we already have A. So A transpose A, because if this is A now, then A transpose A is just going to be the transpose of A. So first row becomes column. So first row is 1, 1, it becomes column 1. Second row becomes column 2. Third row becomes column 3. So all this now multiplied by 1, 1, 2, 1, 3, 1. Okay, so that means we have, because we have two rows here, you have to write each column twice. So 1, 2, 3, 1, 2, 3. Then 1, 1, 1, 1, 1, 1. Okay, then you put this 1, 2, 3 over the top as 1, 2, 3, and then 1, 2, 3. Then down we have 1, 1, 1, and then 1, 1, 1, like this. So A transpose A now is equal to 1 plus 9, 4, that's 13. This is 14 up here. 1, 2, 3. That is 6. This is 6 here. Again, I think this is also 6, right? And this is 3. So 14, 6, 6, 3. Okay, 14, 6, 6, 3, like we got here. Then we also need A transpose B on the other side. So we need A transpose B. So A transpose B. So again, A transpose, we already know that to be 1, 2, 3, 1, 1, 1. And B is 2, 3, 5. 2, 3, 5. So in that case, this is two rows again. So write the column twice. So we have 2, 3, 5, 2, 3, 5. Okay. So then, so that this will now be 1, 2, 3. This is 1, 1, 1. So we have now A transpose B equals 2 times 1, 2. 15 plus 6. 2 plus 6, right? 8. 8 plus 15, that's 23. Then this is 2, 3, 5. So that's 10, right? 23, 10. And that's like the A transpose B thing we got here. That's 23, 10. So finally, then we need to get A and B. So we can then say from A transpose A X equals A transpose B. So this X now will take care of the A and B we are looking for. So A transpose A is already 14663, right? So we have 14663 multiplied by AB, and this is A transpose B also is 2310. 2310. Okay, so this is 2310. Then we need AB, which is simply the same thing as 14663 inverse multiplied by 2310, like this. Because this is a 2 by 2 matrix, we can still find the inverse very easily. So what we just need to do is find the determinant. So we have 1 over the determinant. That's 14 times 3 minus 6 times 6. That's the determinant into, so for these two, we reverse. 3 comes here, 14 comes here. And for the other ones, we just change their signs easily. And then we have 23, 10, like this. So let's see. AB now is equal to 1 over 14 times 3. 3 times, that's 42, I believe. 3 times 4 is 12. Carry 1, that's 42, minus 36 into 3 minus 6 minus 6, 14. Then 23, 10, like this. So that means that AB is 1 over 6, 1 over 6 into 3 minus 6 minus 6, 14 into 23, 10. So we can take care of this now. We can do this. So AB is equal to, of course, this is 2 rows. We can keep the constant first. So we have 1 over 6. So for the 2 rows, now write 23, 10 twice. So we have 23, 10, 23, 10. Okay. Then this is 3 minus 6 minus 6, 14, like this, so that AB now is equal to 1 over 6 into 23 times 3, that's 69, minus 60, then 23 minus 6, that's minus 6 times 3, 18, carry 1, 6 times 2, 12, that's 138, I believe, plus 140, okay, so that AB now can be 1 over 6 into 69 minus 60, that's 9, minus 138 plus 140, that's 2, I believe. So that this can then be 9 over 6, 2 over 6. This is 9 over 6, that's 3 over 2, right? And then this is 1 over 3. 3 over 2, 1 over 3. So y equals ax plus b can then be, what's y now? Y, we don't know. I mean, it's equation, right? So now this is, so a is 3 over 2 and b is 1 over 3. So the equation, the approximation is then a as 3 over 2x, b is 1 over 3. So that's the kind of idea we have right here. Okay, 3 over 2, 1 over 3. So the best line of fit, even though that's not, it's not I mean, that's we can get the best line of it to be 3 over 2x plus 1 over 3, basically. So in summary, we see all of this that uh we in summary, we see that okay, I want to show everything at once. Let's see. Yeah, so the projection finds closest vector in a subspace and error is perpendicular. Then, so that's why where the whole idea of projection and orthogonalization is coming from. Then uses dot products of matrices. Then for least squares now solves inconsistent systems. So normally we saw earlier on that anytime you have more more equations than you have, sorry, when you have more variables than you have equations, yes. When you have more variables than you have no, when you have more equations than you have variables, the system is inconsistent. You can't get the solution. So, but then least squares has given us a way out around it. So it solves inconsistent systems, minimizes squared error, uses normal equations, equals projection onto Coulomb space. So the key formulas for projection, you have A into A transpose A inverse A transpose V. And for least squares now, we have A transpose A inverse A transpose B. This will give you the value of the variables you might be looking for. So we have some practice problems right here, and based on what I've done, you can also follow all this. So I can show them in twos, um, solve the following problems, and show the steps. So projection onto a line, project 3, 4 onto this. So that'll be VU all over UU times U, right? So 3, 4, 1, 2, right? 3, 4, 1, 2. So V is 3, 4. U is 1, 2. So from what we've learned already, we know that the projection of V onto U will just be V dot U all over U dot U multiplied by U. So that means we have V dot U, that's 3, 4 dot 1, 2 all over UU, that's 1, 2 dot 1, 1 comma 2, then 1 comma 2 again. Okay, there's 1 comma 2. So that means we have 3 times 1 plus 4 times 2 down there, all over 1 times 1, 1 times 1 plus 2 times 2 into 1 comma 2. So that means we have 3 plus 8 all over 1 plus 4 into 1 comma 2. So that means we have 11 over 5 into 1 comma 2. So you can leave it this way, right? That the projection of V onto U is 11 over 5 into 1 comma 2, which is the same thing as 11 over 5 comma 11 over 5, right? Comma 22 over 5. And that goes. So you can also project U onto V if you like. So you just change the whole thing. So projection onto a line, you can try that. Projection onto a plane, it's what I did the other time. So you have projection of V to U1, projection of V to U2. That exactly what I did before. Then you do the two parts and sum them together, and whatever you get is the answer. Projection using orthonormal basis. So let U1 and U2 be this. So project V onto this. So of course, same thing. You have project V to U1, project V to U2, and do all the maths and sum it all up. Okay. You can also do this for projection like this. So matrix projection, you can use the formula. I mean, a formula was shown up here before. A into A transpose A inverse A transpose V like that. Then for simple least square now, solve in the least square sense. So here now, you just have 1, 4, 7, 10, 1, 1, 1 like that. And then you do the whole A transpose A and A transpose B kind of thing. So how did you even get B for that one the other time? Okay, we have 1, 2, 3. Okay, nice. So your A now will just be 1, 1, 1 in 1, 1, 1 in 4 places, and B now will be 1, 4, 7, 10, and then you do all the A transpose A, A transpose B, then you multiply, you find the inverse. This is most likely going to be just a unit, so you just do that. Then solve using least squares. Now x plus y is 1, x plus y is 2, x plus y is 4. So this is also an impossible situation, but then you can just form the matrix. This is like 1, 1, 1, 1, 1, 1, and then you have 1, 2, 4 like this. So just use least square also. Then of course you have this data thing, 1 1 2 2 3 2 4 4. So you use least square like what we did. Yeah, so try your hands on all these things. Let me know how helpful this whole thing is to you. And if there's something else you'd like me to try out, feel very free to let me know. If you have subscribed already, I must thank you very much for doing that. And if you haven't subscribed, I wonder why. So why not go ahead, subscribe right away and hit the notification bell so you can always get alerted each time a new video is released. Don't forget to try your hands on these practice questions. All right. Yeah, of course you can also become a member of this channel by clicking on join. That gives you some special privileges. Like, you can have access to my PDF notes on demand. You can hang out with me. We can talk about anything that interests you on my channel. Some videos can be made specially for members, or members can get to see some videos first before other people. You want to avail yourself of the opportunity if possible. Ultimately, don't forget to comment, like, and share so that more people can have access to the great content I have going on here. Till I come your way again, keep doing maths right. Bye.